Greetings, chemistry students. Today we're going to be talking about rate laws for reactions. And essentially, a rate law is an algebraic expression that helps us calculate how fast a reaction occurs. So, it's an expression, a mathematical expression showing how the rate of a reaction changes with concentration or molarity of reactants. And rate laws have to be determined experimentally. You cannot just look at a chemical equation and determine what the rate law is. You can't just look at the coefficients or anything like that and come up with the rate law. It has to be done through experiments. So, as part of this unit, you're going to be analyzing experimental data in order to determine what the rate law is. Rates are always defined as positive numbers. We don't use negative numbers in the rate laws. If something is disappearing, you talk about how fast something is being consumed. You don't talk about the concentration going down in a negative way or anything like that. And with the rate law, there's this thing called the rate constant, which is represented with a lowercase k. And it's very important that you use a lowercase k for the rate constant because a capital K is something else. And the rate constant is temperature dependent. If you change the temperature at which the reaction is happening, the value of the rate constant itself also changes. And then there is N, which is the order of a reaction. Essentially, that's what power the molarities are raised to in the rate law expression. So, for a simple reaction like 2 H2O2s makes 2 H2O plus O2, the rate law is going to be rate equals your rate constant times, and then these square brackets mean molarity, the molarity of hydrogen peroxide raised to some power N. Right? And N is typically going to be a whole number. Sometimes it can be a fraction. But essentially, if N is 1, that means that the rate changes directly with the concentration. As the molarity increases, the rate increases proportionally. If N is 2, as the concentration or molarity increases, the rate increases by that factor squared. So if you doubled the concentration, you would quadruple the rate. If you tripled the concentration, the rate would go up by a factor of 3 squared, or by 9. If N is 3, that would be a third order reaction, then whatever you do to the concentration, the rate happens cubed. And if N happens to equal 0, that means that the rate is completely independent of the concentration of that reactant. And 0 order reactions definitely do happen. Now, there are two types of rate laws. There is the differential rate law, which is the one I was just referring to on the previous slide. It's also just known as the rate law, and it shows how rate changes with concentration. And then, as we'll see later, there's also what's called the integrated rate law, which shows how concentrations change over time. For those of you who have taken calculus, these terms will seem very familiar to you. For those of you who haven't, don't worry about it. Right? Now, for both of these rate laws, we only include reactants. That's the things on the left side of the arrow in the chemical equation. Do not put products in the rate law. So now let's look at how we determine the rate law. And we're going to use the method of initial rates. So based on several experiments where we vary the concentrations of the reactants, we will determine how the initial instantaneous rate changes based on the manipulating the concentrations. I don't know what just happened. Okay, there we go. All right, so if we wanted to compare rates, so you take for two trials that you have the rate in trial 2 divided by the rate in trial 1 equals the concentration of that substance in trial 2 divided by the concentration of that substance in trial 1 raised to some power N. Right? So it's rate 2 over rate 1 equals concentration 2 over concentration 1 to the power of N. And then the last thing for you to know is that you may be asked what the reaction order is for a reaction, and that's the sum of the exponents in the rate law. All right. So we're going to take a look at this experiment. This is initial rates from 3 experiments for the reaction NH4 plus nitrite makes nitrogen plus water. Here we go. So we're going to look at the initial rates from 3 experiments for this reaction, and this should say NO2 right there. So if we compare experiments 1 and 2, what you'll notice is that the concentration of NH4 plus does not change. So we're just going to ignore NH4 plus for right now. And so what we're going to say is that rate 2 over rate 1, so 2.7 times 10 to the minus 7th divided by 1.35 times 10 to the minus 7th equals the concentration of NO2 in trial 2, 0.01 divided by 0.005 to the n. And when you simplify this, you'll get 2 equals 2 to the n. So n equals 1 because 2 to the first power is 2. So it is first order in NO2 minus. So now let's compare experiments 2 and 3 where the NO2 doesn't change. So we can ignore it. So we're going to compare experiments 2 and 3 for the ammonium ion. So we take 5.4 times 10 to the negative 7th divided by 2.7 times 10 to the negative 7th equals 0.2 over 0.1 to the n. That comes out to be, once again, 2 equals 2 to the n, where n equals 1. So it's first order in NO2 and it's first order in NH4 plus. So that means that our rate law simply is rate equals K times the concentration of NH4 plus times the concentration of NO2 minus. And they're both raised to the first power, and you don't have to write the ones for the first power. Then, if we wanted to figure out what the value of K is, then we would pick any one of these trials we want, and we plug in the numbers. So let's just pick, I don't know, the second trial, because those numbers look a little bit easier to deal with. So we take 2.7 times 10 to the negative 7th moles per liter second equals K times 0.1 moles per liter times 0.01 moles per liter. And then to solve for K, we're going to take the 2.7 times 10 to the negative 7th divided by 0.1 divided by 0.01. And I'm getting 2.7 times 10 to the negative 4th. And then our units are going to be liters per mole second. Because we have moles divided by moles divided by moles, so one of the moles cancels the other one out, and we end up with moles on the denominator. And then we have liters on the bottom twice being divided into liters on the bottom, so liters moves to the top. So this is ultimately what we get when we solve this, including units. And so then if we wanted to do another trial, if we wanted to figure out what the rate is initially at a different set of concentrations, we could just plug them into our rate law with our value of K and solve. Now, this value of K is only good for whatever temperature these 3 experiments were done at. If we change the temperature, everything else changes, right? So that's as far into the notes with that as we're going to go. I'm going to show you another experiment here. I'm going to show you another worksheet where we're going to consider some problems that we're going to look at. I'm going to walk you through this first one. Now, for some of this, you may not even have to use the math equation. You may just be able to do this with your words, because you can write about it. So if we're asked to determine the order of the reaction with respect to hydrogen in this experiment, well, you'll notice that chlorine stays the same between experiments 1 and 2. The hydrogen concentration doubles. The rate doubles. So what you would say is in experiments 1 and 2, the H2 doubles, as does the rate. So that is first order. I mean, whatever happened to the concentration, the same thing happened to the rate. Now, if we you could also do the formula. You could take 3.6 times 10 to the negative 12th over 1.82 times 10 to the negative 12th, which is going to be 2, equals 2 to the n equals 1. You can do the math. For B, if we want to compare and see what happens here, we have this trial between experiments 2 and 3, where chlorine is cut in half, the rate gets cut in half, so that would also be first order. So then you could write the rate law. So rate equals K times the concentration of hydrogen times the concentration of chlorine. Then for the units, that's where you would plug in the moles per liter per second and the moles per liter and the moles per liter and solve. You could also find the value of the rate constant. And then for part E, it's asking you to find what the initial rate would be when they're giving you some concentrations. So you're going to have to find the value of K and plug in for that.